Welcome to the Low Power Optimization chapter. Most microcontroller applications spend over 90% of their time in sleep mode, only waking up when absolutely needed, such as when motion is detected, or periodically to, say, sample the air for smoke detectors, or maybe when a button is pressed on a remote. Msp430 has pioneered ultra-low power microcontrollers. This chapter discusses many of the techniques and tools that you can use to minimize the energy when designing with them. Please note, in order to keep the video short, we may have abbreviated the content in the chapter. To view all of it, please refer to the workshop's full PDF file. You'll find it listed on the wiki page under Download Workshop Files as Student Workbook. This chapter consists of 4 major parts. First, we discuss low power modes, as they are the most obvious low power technique. Next, we'll describe a few concepts that demonstrate how to go about designing low power embedded systems. Third, we'll look at the ULP Advisor tool along with its set of rules that it applies when examining your code. Finally, we describe TI's energy trace technology. Unlike the previous parts of this chapter, energy trace is actually a measurement tool. We can use it to provide feedback on how well we're implementing the other techniques in this chapter. The chapter ends with a lab exercise and an appendix. We start the chapter out with the state flow diagram of the Msp430 operating modes. Earlier in the workshop, we described the first 3 modes, bore, pour, and puck, and how they take the CPU from reset to actively running. This chapter focuses on the bottom half of the diagram. Each of these additional modes provides a successively lower power operating state, from LPM 0 to LPM 4. In just a minute, we'll examine exactly what gets turned off in each of these low power modes. One thing to notice about the Msp430's low power modes is that they are simple to get into and out of. Unlike some other processors, the Msp430 makes it easy to enter and exit a low power state. In fact, changing these modes is simply done by changing a couple of bits in the status register. Some other processors even require that you enter one low power state in order to reach another, which is clumsy and difficult. With the phrase low power is in our DNA, we had to make low power modes easy to use. But wait, there are 2 more modes which are even lower power. Some generations of Msp430s also offer the 0.5 low power modes. These modes also turn off the processor core's internal voltage regulator, in addition to all the other low power tricks applied by LPM 3 or LPM 4, thus saving even more energy. Of course, these modes are only available on those devices that contain on-chip voltage regulators. You might remember we discussed voltage regulators back in the chapter on clocking and power management. The main difference with the LPM 3.5 or 5.5 modes, well, beyond being the lowest power states on the Msp430, is that because their voltage regulator is turned off, exiting them results in a brownout reset. If you're using one of these modes, you will want your boot routine to check if you're restarting the CPU from a brownout or from one of the .5 modes. Okay, what actually gets turned off in each low power mode? Well, here's a table that shows us what features are enabled and disabled in each of the low power modes. As we work down from active mode, we see that each of the Msp430 internal clocks gets turned off at different low power levels. For example, M clock, the CPU clock that is, gets disabled right away at LPM 0, but the low frequency A clock stays on all the way through LPM 3. Turning off each of these clocks saves power. There are 3 other things to notice on this slide. 1. The RAM is powered in every state except the 2.5 modes where the voltage regulators are disabled. By the way, some later devices let you disable all or individual banks of RAM in addition to these modes. 2. The brownout reset peripheral is always on, which is a good thing. And finally, 3. The table shows that the Msp430 can wake itself up in all but the LPM 4 modes. This actually relates to the adjacent interrupt sources column. Except for LPM 4 and 4.5, there can be internal peripherals running which can be used to wake the CPU from a low power mode. But these 4 and 4.5 modes require some external event in order to wake them up from sleep. As a final note, many low power enthusiasts really value TI's FRAM based processors because FRAM can be used like traditional RAM but doesn't lose its contents, even in LPM 3.5 and 4.5 modes. In fact, for many users, FRAM has actually made these lowest power modes more usable. The table on this slide shows us a couple of different things. One, it compares the power savings for most of the low power modes we just spoke about. It also provides the wake-up times from those low power modes. Second, it gives us a rough comparison of the low power mode differences between various generations of MSP devices. Please note, though, that you should always refer to your specific device's datasheet for the most accurate information. From this table, though, we can see that the FR58 and 59 devices really are the lowest power CPUs. TI has done a really good job eking out all of the power from these low power modes. Oh, and they've also found new tricks in waking them up quickly. By the way, if you think the G2XX numbers look good, they are. But remember, devices such as the G2553 do not include the on-chip voltage regulator, which does let them wake up more quickly. Okay, now that we've seen how good these low power numbers are, how do we enter the low power modes? Using the TI compiler, the easiest way to enter a low power mode is to call its associated intrinsic function. For example, the low power mode 3 function shown here. Alternatively, you can enter a low power mode by writing directly to the status register. This involves using the bit set status register intrinsic function. In the example shown here, for LPM 0, we're setting the global interrupt enable bit as well as the LPM 0 bits in the status register. Both methods shown here will achieve the same goal of entering a low power mode with interrupts enabled. The low power mode function is a bit easier to read, although the status register function provides slightly more flexibility. Nice thing is that you can choose whichever suits you. Okay then, how do I exit low power mode? And can I automatically re-enter LPM, or do I have to keep explicitly calling one of the low power mode functions? As we see in this example, once we place the CPU into a low power mode, such as LPM 3, it will stay there forever. Well, that is until an interrupt occurs. When an interrupt wakes the CPU, the processor leaves the low power mode and enters an interrupt service routine. In the ISR, the Msp430 automatically saves the status register and program counter and then returns to the active mode, turning on whichever clocks were shut down by the low power modes. It then executes the appropriate interrupt service routine. So, what happened when the CPU returned active mode? Oh, it automatically saved the status register by pushing it to the stack. And why do we care about that here in the low power mode chapter? Well, if you remember from a few slides ago, the bits that put the processor into a low power mode are located in the status register. This means that as we enter the ISR, we're actually saving the operating mode the processor resided in before the interrupt, a fact that will be really important here in a minute. At the end of the ISR, the compiler calls the return from interrupt assembly language instruction, and this not only restores the program counter, putting us back to whatever code we were running before the interrupt, but it also restores the status register. Wow, that means our device automatically goes right back into low power mode without us having to do anything. In fact, in this example, we don't even need a while loop. As written, once the CPU enters LPM 3, it will stay there except for when it's servicing an interrupt. That's cool, and it just goes to show what we said before. Low power is in our DNA. Okay, so all of this is great, but what happens if I want to come out of a low power mode and return to my main routine after an interrupt? I mean, we said in the interrupt chapter that we shouldn't do a lot of heavy-duty processing in an interrupt service routine, so how can I get back to main to perform my follow-up processing? Here's an example that shows us how to get back to our main code and leave a low power mode after an interrupt. In this case, it looks like we want to run a filter algorithm after the ISR, then re-enter the LPM 3 mode. The key to leaving LPM after an interrupt is to call the low power mode off on exit function somewhere in your ISR. This will disable the feature that automatically returns you to the low power mode. Since we called this function in the example shown here, the compiler clears the low power mode bits when returning from an interrupt. As you might expect, this means the CPU starts executing whatever code follows the low power mode 3 function, which in this case is the filter function. Once the filter function is run, we turn around and return to the top of the while loop and enter the LPM 3 mode again. Well, that is until the next time the interrupt occurs. There you have it. You can either re-enter LPM automatically, as we showed on the previous slide, or not, as we show in this slide. Thus far, we have discussed how low power modes can be used to lessen the energy used by the processor. What other techniques are there for minimizing our system's usage? That's what we'll explore in the next section. If reducing the power footprint is a goal of yours, we've tried to do that by making the Msp430 an ultra-low power processor. That said, how you use the processor has a big impact on how little or how much energy actually gets consumed. Even if low power isn't a big consideration for your embedded system, remember, even wall-powered devices can, and maybe should, become greener. Next, let's look at some of the principles of low power operation. As we've just seen in the first part of this chapter, low power modes and interrupts go together. Used appropriately, low power modes can help extend the battery life in your system. Visually, how might this look? Since most embedded system designers already use interrupts to control the flow of their application, half the battle is already done. With this in mind, we can put the processor into standby while waiting for an interrupt event. Shown here, and as we already saw earlier in the chapter, standby modes like LPM3 can help you save a lot of power. Maximizing our time in LPM3 means you can get by with just a clock using only a simple 32 kHz crystal. Then, when an event occurs and there's real work to be done, the DCO starts quickly, letting M clock power the CPU through all the needed calculations. When the work is done, we return to saving power. In this way, the CPU's active state can be kept to short bursts, only consuming the minimum energy required. What's another trick to saving energy? Our next trick is, don't turn on the CPU. Okay, so the bullet says, replace software with peripherals. But the underlying principle is the same as the previous bullets. Keep the CPU off as much as possible. Bottom line, a fixed function, hardwired peripheral should be able to complete its job more efficiently than a software programmed CPU can do the same job. For example, a timer peripheral is more energy efficient than a CPU counting in software. To that end, let's use the peripherals wherever we can. For example, try using the timer to tell the A to D converter when to sample the input. Then, once the conversion is complete, let the DMA store the result to memory, only waking the CPU when a block of samples are ready for processing. Unfortunately, not every Msp430 has all of these peripherals that can be chained in this way, but make use of them whenever possible. Not only can this save you power, but direct connections such as these can be more precise and minimize latency. For example, when the CPU is used between the timer and the A to D converter, there is a small time delay while the CPU recognizes that the timer interrupt has occurred, and then it has to vector to the interrupt and begin executing the ISR. As small as this delay is, we can improve the determinism and minimize the latency by using direct connections wherever possible. Our next two suggestions: don't leave pins floating, and don't forget to turn off unneeded external system components. It's hard for us to recommend how you should manage external devices in your system. Most likely you will handle these through GPIO pins or maybe serial communications. It just depends on how your system is configured. But we can take a look at what to do with unused pins. If pins are configured as inputs, which is generally the default state for most processors, their state can end up floating up or down if left unused or disconnected. This floating state will consume power. In fact, we'll see this in the upcoming lab exercise. To eliminate this wasted energy, you should configure any unused GPIO pins. You can either 1. Leave them set as inputs and drive them high or low externally. 2. Set them as an input but use the internal pull-up or pull-down resistors. Or 3. Configure the pins as an output. In many of the Msp430 devices, you can choose any of these and get the same low energy benefits. But, as we found when writing the lab exercises, some devices actually do better with one option versus another. That's why it's always good to check your results using tools like TI's Energy Trace. The point made with this bullet is just an extension of what we've already talked about in this chapter. How can we get the CPU back to sleep as quickly as possible? Efficient code will help us do that. Every instruction we eliminate is another cycle spent in sleep, but it's also one less instruction we have to fetch, and memory fetches cost energy. What then are some concrete things we can do to get back to sleep more quickly, as well as maximizing CPU efficiency? Power dissipation increases with frequency, voltage, and temperature. Therefore, you may want to consider lowering the input voltage or clock speed in your system. Be careful though, as there is often a lot of diminishing returns. Running too slowly may end up taking more energy since you're running the CPU longer. The Msp430 community seems to agree that an 8 MHz CPU clock rate is a good compromise between power and performance. So that may be a good place for you to start, but if you're taking low power to the extreme, it probably warrants doing some energy benchmarking for your system. Another suggestion for improving processor efficiency is to make use of whatever accelerators and libraries are available. It's hard to beat a hardwired accelerator when it comes to performance and efficiency. For example, while the compiler, by default, uses the MPY peripheral, you will need to write code to access the other accelerators. Next, don't forget to use the compiler's optimizer. It can be used to tune for code performance and/or size. The TI compiler even provides an optimization advisor. Check out its video tutorial on the TI website. Finally, the Msp430 Applications team provides a number of other libraries. Not only can these make your coding easier, but they've already been optimized for you. Check them out inside the MSPware package. We are well over halfway through the chapter. It's now time to focus on two tools that can help you achieve lower energy usage. Let's start with the ULP Advisor. As we've shown here, using ULP Advisor is the last of our low power suggestions for this chapter. In this section, we'll talk a little bit about how it works, as well as outline the list of rules it employs. TI has done its best to optimize the Msp430 silicon to provide you with the lowest power MCU in the industry. And we expect that your hardware design team is doing its best to cut every little bit of excess power too. But that really only makes up half of the low power story. You have to power optimize your software too. In fact, power optimizing your software is what this whole chapter is about. When TI talks about low power, we realize that the real effort doesn't end with how many nanoamps it takes to perform a multiply. To make an effective low power embedded system, you need to have the tools to observe and optimize your software in order to achieve the lowest power energy usage. And that's just where the TI ecosystem shines. You know, though, these tools aren't just for beginners. Sure, ULP Advisor is a fantastic tool for those developers just learning about ultra low power design. The compiler analyzes your code and provides immediate feedback. What a great way to learn! But, as any good tool should, it also helps those of us who are experienced ULP developers. Even the experts will forget to check their code practices sometimes. Or, there may be so much code that it's great to have an automated tool to help you work through all of it. Like all optimizers, you will probably want to ignore its advice while you're getting your program working, just as we've done in the earlier workshop lab exercises. But once you've got your code operating correctly, and it's time to apply optimization, this tool is invaluable. Regardless of your experience level, this tool will help you find areas in your code that can be further power optimized. How does the tool work? It's a static analysis tool. That is, it works through your code line by line and checks it against a best practices ULP rule list. As it finds areas of improvements, it identifies where in your program an optimization might be helpful, while also providing a link to the TI wiki page that describes the associated rule and ways you might tweak your code. The feedback is provided as remarks as opposed to errors or warnings. You don't have to heed the advice, it's just there to provide a hint. So with all of this in mind, what are the rules? Don't worry, we won't take the time to read each rule to you. Remember, there's a TI wiki page that provides an in-depth explanation of each. What we've done on this slide is to try and combine the rules into groups. We hope that these might help you see them from a larger perspective. Looking at the first group, you'll see that these cover many of the items discussed earlier in this chapter. For example, if you don't enter a low power mode somewhere in your code, the optimizer will point this out to you and suggest that you should do so. By the way, if you found a trick to writing better ULP code and think we've missed a rule for it, please head over to the ULP wiki page and submit it. We're always hunting for more smarts to add to our code and tools. Don't worry if you're not using the TIC compiler. Like most of TI's coding tools, ULP Advisor works with IAR systems and the GNU GCC compiler too. Finally, before we move on to the last section in this chapter, here's a screenshot showing how to configure ULP Advisor for the TI compiler within Code Composer Studio. First of all, there's really nothing you need to do. ULP Advisor is turned on by default. Even so, we've shown here the ULP Advisor command line compiler option as well as the CCS GUI configuration dialog. By the way, one thing the GUI clearly demonstrates is that you can turn off any one or group of rules that you don't care about. Finally, let's turn our attention to the new Energy Trace Measurement tool. As of the writing of this chapter, there are currently two tools which support energy trace measurements. One, the FET emulator on the FR5969 Launchpad, and two, the brand new Msp430 emulation pod and cable, which can be used with any system that supports the Msp430 4 or 2-wired JTAG debugging methodology. For example, in the upcoming class exercise, we recommend that the F5529 USB Launchpad users use the Msp430 so that they can obtain energy trace data. Both of these tools were released in June of 2014. In the future, most Msp430 development boards, which include onboard emulation, will support energy trace technology. One other quick side note. FET stands for Flash or FRAM emulation tool. Nowadays, though, most of us just think of it as the name of the Msp430 debug and trace tool. Lastly, we shouldn't forget to mention that there are two levels of energy trace feedback. The first, called energy trace, provides you with highly accurate energy measurements. The second, called Energy Trace++, extends the energy measurement feature by providing you with correlated information regarding which low power modes, peripherals, and clocks are running in your system at any given time. Since the Energy Trace++ requires additional features in the device silicon, as of today, this is only supported by the FR58, 59, and 69 devices. If you're using the FR5969 Launchpad, you will be able to see this extra information during the upcoming lab exercise. Okay, what does this energy trace data look like? Here's an example of an energy trace profile. This data is taken from an actual running system. In fact, in the 10-second capture period, it appears this system consumed 72.26 millijoules of energy. The tool provides a number of other items which you may find useful or critical in your development. Hey, it even estimates how long the system can run on a CR2032 battery. Please note, though, that this example was captured before we started power optimizing our program. Okay, so then what does the Energy Trace++ information look like? Here's an example of an Energy Trace++ display captured for the FR5969 device. We've shown two tabs of the interface here on this slide. The left provides a summary of the energy used, while the right screen shows the active system states over time. But wait, there's more. Whether you're an Energy Trace or Energy Trace++, the TI tools provide graphs to show the instantaneous power usage as well as the accumulated energy usage over time. Finally, there's one more feature that we found useful when trying to power optimize our code. The tool also allows us to compare our current energy trace profile with the previous reference profile. This lets us see how much our power optimizing has saved us, or not. Surprisingly, sometimes after we've tweaked our code thinking we'll lower the power, the tool shows us that it got worse. It's nearly impossible to get the most efficiency without good feedback, and that's just what this tool provides. Thankfully, in this case, it looks like our efforts paid off and we saved 68% of our energy compared to our previous run. How does Energy Trace measure energy so accurately? The patented answer is so simple, you'll probably be like me and wonder, why didn't I think of that? At the heart of the emulator pod, which TI calls a FET for Flash or FRAM emulation tool, is a DC to DC power supply. As with most MCU emulators, the FET provides power to the target system being debugged. The magic comes from how the DC to DC voltage regulator works. Power is transferred across the regulator via pulses of energy. When the target system needs more power, this is handled by increasing the frequency of pulses from the input to the output of the regulator. Since the power supply is under software control, that is, since we control the power supply with the TI microcontroller, all we have to do is count the pulses to know how much energy is being used by the system. Yes, it's just that simple. But not only is this simple and efficient, but it's considerably more accurate than the old-fashioned way of measuring energy with a multimeter. In the past, most of us would probably use this method, which essentially samples the current drawn across a resistor. While this does work, it can miss the fine details needed when you're constructing an ultra-low power application. As we know from earlier in this chapter, we often design our systems to wake up, perform a task, and go back to sleep very quickly. With the old-fashioned multimeter approach, if we're too quick with our system, our meter won't even register that we've drawn energy. We could wake up, go back to sleep between the samples. Unfortunately, this would mean that our power estimates would be inaccurate, and our marketing team would probably be unhappy with us. Since the TI-FET emulator controls the energy pulses, it won't miss capturing every little bit of energy data. What are the lab exercises for this chapter? The lab is broken down into 3 parts. Part A gets us started with energy trace. That is, we begin the lab learning how to measure energy usage in the system. Part B then has us turn on the ULP Advisor and start power optimizing our code. Finally, Part C asks us to use our new skills to examine and fix the energy wasted by floating pins. One last thing before we send you off to play with the tools. Let's review your options for measuring energy in this exercise. 1. If you're using the FR5969 Launchpad, you're all set to go. Your Launchpad already supports energy trace. On the other hand, if you're using the F5529 USB Launchpad, you will need some additional hardware to measure power. If you're taking a live workshop, your instructor should have an Msp430 that supports energy trace that you can use with your Launchpad. Please see the appendix for this chapter to figure out how to hook up the Msp430 to your Launchpad. B, if you're at home, we highly recommend that you purchase the Msp430 so that you too can get access to the accurate energy trace data. Your other option is to fall back on the old-fashioned multimeter approach. As we reference at the beginning of the lab instructions, the F5529 Launchpad User's Guide explains how to perform power measurements on this board using a multimeter. That's it. Go off and play with the power optimization and hopefully energy trace tools.